So welcome. We're going to move, we've been talking about DC only circuits so far, so a fixed 5 volt or a fixed battery or a fixed amount of current that's going into the current sources. So now we're going to move to components that actually use AC. So they vary over time and they actually change and are time dependent elements. So AC is alternating current. So this is a sinusoid. It's going to be a varying voltage over time. So the learning objectives today is that we're going to look at some circuits that have these types of components, capacitors and inductors. So the C here is for capacitor, and the L stands for an inductor. So with these are what are called first order differential equations when they have a resistor and a capacitor or a resistor and an inductor. We're going to also learn about what a time constant tau means, and we're going to be able to calculate the Thevenin equivalent seen by a time dependent element. So these time-dependent elements are the capacitors and inductors. So both of these are time-dependent elements. So the method to do this, which we're going to practice, is to redraw the circuit for 3 different instances. Before a change happens, which would be 0 minus. So this is going to be your before change. The initial is going to be at the change. And then a final value will be a long time after the change. So instead of having to do a full solution for a first order differential equation, instead we can actually use a form of the general solution that we know it will be, and then we can analyze the circuit for these 3 time periods, and then we can use those to be able to solve the full equation. So right before a change, I should say. So the initial 0 minus is right before a change happens. 0 plus will be at the change time, and then final would be a long time after the change. So to understand this, we have to understand the capacitor and the inductor and what happens right before a change, right at a change, and right after, and a long time after a change. And then the final thing that we're going to do is be able to solve for a voltage across a capacitor in a given circuit that is now time dependent. So we're going to have these functions that are dependent on time. So what does happen with a capacitor and an inductor? So a capacitor equation, so these are going to be ones you're going to have to memorize. So for those of you who are just concurrently in Calc 1, the derivative is probably a little newer to you. So this is now your application of a derivative. So what this means is that you have a change in voltage with a change in time. So dV dt. So your current is actually a function of time, and your capacitance is a fixed value. So this is going to be a fixed value. And capacitance, capacitance units are in farads, and it will be an F, farad. The unit for an inductor is in henries, H. So those are the units for capacitance and inductors. And then, so the C is going to be a fixed value, but the voltage will vary over time. For an inductor, again, memorize So memorize this equation and memorize this one. For an inductor, the voltage is going to be a function of the inductance that's fixed, and then it's the change in current over the change in time. So what happens if it's sat there a long time and there is no change? If there's no change in voltage over time, so you've taken out a capacitor from the drawer, it's sitting there. It sat in that drawer for a long time. What is dV dt? It's going to be 0, correct. So which means what? Current is 0, which makes it look like a open circuit. There you go. So that's how we're going to look at these, is we look at that equation and we look at, okay, well, if it is sat there for a long time, whether it's in a drawer or it's sat there in a circuit and there's now no more change in time. So if I put a DC voltage up to a capacitor, right before I connect it, it's going to be 0 current. Right as I connect it, that has to stay fixed for that moment, but then it's going to start to charge up to the battery value. So the voltage there, right at the initial time, it can't change instantaneously. So that's the characteristic that you have to understand, is it can't change instantaneously. So it takes it a minute to charge up to the full value of the battery. But once it reaches that battery value, there's no more change over time, and that goes back to 0. So now it's going to look like it's open, but it's going to have a fixed voltage across it. So it actually can store charge. So this is one way to think about this, is it stores charge. And that in turn looks like a voltage. The inductor is a little bit different in that it's hard to see this, but it stores current. Yes?
So are batteries basically capacitors? They store charge? Or what is the purpose of storing charge other than like batteries in a circuit?
So yes, it kind of can be like a battery, but the issue is that it will, so a battery itself has a chemical reaction that's constantly changing. And so unfortunately with this is ideally, yes, a capacitor could be a battery, but because we live in a real world, there's going to be some little bit of connections to something else, or there'll be what's called a parasitic effect, where it will couple with something that you don't want it to and create a dissipation of something. So over time it will actually discharge if it doesn't constantly have that connection. So you can't use it as a battery solely. You can charge it up and then use that until that voltage is gone, but it will actually dissipate over time.
I'm sure we'll talk about it more later, but like what he was saying, is it just like a battery? Isn't the point of it to kind of protect against fluctuations in the power source or whatever? Or
Correct.
maybe one use of it.
Uh-huh.
It stores a little bit of extra voltage, so if there's a fluctuation, there's no disruption in the circuit.
Yep. So that is one way that you can use it, is to put it across. Well, you'll see it a lot of times, yes. It will be put across a location in a circuit where you want to keep that fixed voltage. So if there is any fluctuations, yes, it will stay there, and then it will change slightly, but then the battery will come back on, and then it will go back up to the full amount.
So does that have anything to do with AC/DC adapters then? Or is that not?
So it's used in AC/DC adapters, but not solely by itself.
Okay.
Right. Any other questions about the capacitor? Okay, so now we get, so inductors. So an inductor is a little harder to visualize because we all understand batteries. So storing voltage sounds, that makes more sense because a battery. Current storage is a little bit harder to understand, and that's the way that the inductor actually works. So in Physics 2220, you guys will learn, if you haven't taken that yet, but you learn about magnetics. And so that electromagnetic field is actually what happens with an inductor. It creates a field around it, and then it pushes the current movement. Because remember, movement of current is the change in positive and negative charges. And so it creates this field and it creates this current flow. And so it's kind of like if you think about it as water and current as water, it's kind of like a water wheel. But instead of a water wheel, it's current that's going on. So it's moving the current this way, or it could actually move it the other way. So it can go both directions depending on which charge is where on the inductor. So plus or minus to plus. So it's actually interchangeable with and both of these are, the capacitors can also be interchanged with whichever way you're putting on the voltage storage to them. Note that in your lab kits, there'll be some, and it will have a plus and minus. And then in a schematic, you may actually see a capacitor with a little curvature to it. That means the negative side. So this would always be the negative side of this. For these capacitors, you do need to be very careful to hook them up correctly to have the positive on the more positive side and the negative on the other. Otherwise, you'll blow them. And it will smell really bad in the lab. And every year we tend to have somebody blow up a capacitor. So do note that some of them are polarized, meaning that there is a defined plus and minus. They're usually the bigger capacitors, and you will see a big minus around the minus side on them. So you'll know which lead on that capacitor you need to hook up. But just note, like, that is one. Another thing is if your capacitor has one side shorter than the other one of them's going to be negative. So that will be a polarized capacitor.
How do they make that? Like, because isn't it just like a sheet of metal, like, or something conductive with something in between it? So how do they make one side designated positive?
So they use different materials. So they are actually different materials on them. So some of them are dielectric difference and some are the metals that are used on each side. So that's why there is a charge difference on them, is that the materials are different. If they were the same, which are what most of them are, then it's interchangeable. But in these that are polarized, there is an actual difference in material on them. All right, so the inductors, we think of it as storing current. And I know that one's a little harder to visualize. So with this one, what happens when you have taken it out of the drawer, it's sat there for a long time, you have no change in current over time, right? So what happens here? So no voltage, which means short circuit, correct. So this is how we're going to model these. So these are easy, open, short. So those two things make the circuit really easy, and all we have to do is replace the capacitor whenever it sat there for a long time as an open circuit. So right before a change, it's going to be open because that sat there for a long time. Right at the change, it's going to actually act like a voltage source. So it's going to act like an open circuit after sitting for a long time. So we say this is the time right before the change and the time at infinity. For at the change, it's right at t equals 0 plus. You replace it with that voltage source with the value found at t equals 0 minus. Yes?
For the part where it's the open circuit, do you mean that t is 0 minus or t is infinity?
At both of those, and. So both those conditions, because it's sat there a long time before a change happens, and then a change happens. So during the change, you're going to model it as a voltage source. and then it's gonna sit there again for a long time, and then you're gonna analyze it just right at like a really long time later. For the inductor, it acts like a short, so it's gonna be a short after sitting a long time. So again, it's going to be at both t equals 0 minus and t equals infinity, both. And then this one is going to be a current source. And the value is I at t equals 0 minus. So it's the current that you find after it's sat there a long time. Yes?
So for both of these elements, so like for the capacitor, if the capacitor is receiving a steady amount of voltage, like there is no change, wouldn't that also make it an open circuit, an open current, because the derivative of voltage is 0?
Uh-huh. And so that's why we look at it as open, but right at the change, which is really literally right that second, and then it changes and becomes again an open. So there's a small little time period just because it can't change instantaneously. So because these are real circuits and that material takes a second to, or we're gonna talk about how long it takes, but it takes it a little bit of time to be able to make that change to then it's open again. So right at that moment, it can't change instantaneously. We use the value right before it changes, and then we use it right at that time, and then we know, yes, it becomes open again. But there's that small little increment just because of the characteristics. It's a physical device. It can't change instantaneously. Does that make sense? So theoretically, yes, it does never have that, but realistically, it's a physical device. And those material, once you put on a voltage to two plates, it takes it a second for the migration of the electrons to move. And because of that limitation of a physical device, we get this time period of where, yes, it still has that same voltage on there for the capacitor, and then it will have the same current flow for a second, or less than a second usually, for a really short time period, but that's how we analyze what is that value. Does that make sense?
Yeah.
Okay, yes?
So would it be like when it is charging and not like charge? Like I'm just confused, like below. Oh, yeah, I'm thinking like here. Like so, like when it's like in the instant that it's charging. So like when you have the capacitor, it's dV is positive. Is that what it means? In that instant? I'm just kind of confused, like what you're saying, like instant.
So theoretically, let me draw some graphs here. Okay, so we're using t as 0 as like, okay, this is when a change happens. So thinking about a capacitor that sat in a drawer for a really long time, so it has no connection to it, it has nothing on it, 0. So it's easy to say like, yeah, it's 0. So there's nothing on it, and then say we hook it up to a battery. So let me put it to a 5-volt battery. So we take it out of the drawer and we hook it up to a 5-volt battery. So what happens here if we hook it right up to a 5-volt battery? It can't change to be 5 volts immediately, right? It takes it a second to get up to 5 volts. And then there's not going to be any more change on it. So we call these time periods, this would be called a transient state. And then when it is, again, yes, it will be open again once it reaches that 5 volts, because then now there's no more change. This is called the steady state. So this transient state is kind of what I'm talking about, where it does take it a second physically to come up to 5 volts.
Okay.
So same thing with the inductor, as far as the current flow. So the voltage, anyway, it's the same kind of idea. It will charge up or it will discharge. So both of these, yes, they'll be charging or they'll be discharging, depending on like when you're looking at the circuits. All right, any other questions? Hopefully this will make sense when we start to look at actual circuits. Okay, so this is just basically what we just said, but I just kind of combined them in the previous ones. Okay. Okay, so what do you guys think? The voltage source gets turned on. In this case, we now have a resistor to it. If we wait a long time, what is true a long time later? The current becomes a positive non-zero constant. The voltage across the capacitor becomes a positive non-zero constant, which would be B. Both current and voltage become a positive non-zero constant, C, or there's no voltage and no current across the capacitor, D. So it's sat there for a really long time, so what do you look at the capacitor as? Open. So if we remove this and it's open, is there current? Okay, good. So no current, so zero current. So it's not A. Is there a voltage there?
Yeah.
Yes, because you have no drop across R because there's no current, but there's still the fixed voltage. So this voltage will be V also, right? Between the plus and the minus side. So there is voltage across it. This one is no, because you can't have both current and voltage becoming positive because there's no current, but there is voltage. And this one is not true either. There's no voltage and no current across the capacitor. All right, does that make sense? Okay. All right, what does the voltage across the capacitor stabilize to? Kind of already gave this away, but okay, V. All right. Okay, so now we're going to look at the actual circuits. And when we look at the circuits, we have to use I equals C dV dt. So we have to use that the current actually is a differential. So these are not very pretty in the time domain. So later we're going to learn a technique to actually move out of the time domain so we don't have that differential in there. It makes it much easier. But for this one, we are going to analyze it just like we would another circuit, but we are going to, well, first off, knowing that, so RC and I naught are fixed known constants. We don't know VC, so that's what we're trying to find here. So we're going to write our equation. So we know the current in this branch is C dV C dt. What's the current here? And we're going to close this. So this symbol that you just saw is a switch symbol. It has the arrow meaning that at time 0 it will be closed. So right before that it will be open. So with this closed, what's the current in this branch? Yes, Peter.
Wouldn't it be I0 minus C?
Okay. So you could say that this current is,
With the current law or ECE?
yep, so going, if we want to do it down here, so going in is I naught, going out is I1 and C dV C dt. So I1 would be I naught minus C dV C dt. Or we can use Ohm's law there. we're trying to solve for VC, so this could also be written as VC over R.
Oh, yeah.
So either way, I mean, neither one is wrong, so they're both just different ways of writing the same thing. So, you know, with this, we can also rewrite this current summation as VC over R, since we're trying to find VC, is equal to I naught minus C dVC dt. So now we have just the one unknown variable VC in it. So multiplying to get rid of the R, we have VC, and taking them all over to the other side to get equal to 0, minus I naught R plus RC dVC dt equals 0. And that leads me to what's called the separation of variables to solve this. So what you do with separation of variables is that, well, I guess I'll back up 1 second. So this equation itself is called a first order differential equation. The order refers to how many derivatives you have in there. For every element we have in a circuit, we're going to get one order of differential equation. So if you have 5 capacitors or 3 capacitors, 2 inductors in your circuit, you're going to get a 5th order differential equation. These are not pretty to solve in the time domain. So we're going to learn techniques on how to not solve them in the time domain. So I'm going to go, like, there's a video if you want to go through this whole derivation of the separation of variables. The idea of it, though, is that you combine the 2 different variables. So here meaning variable of VC is one variable and T is the other variable. And so putting all the time constants on, or time on one side, and then combining all the VC on the other side, you can actually then integrate and solve this to find the form of this particular circuit. So if you have interest in that, you're far enough in math to understand it, feel free to go watch that video. Otherwise, what we're going to use from this is this end result of a generic form. So this ends up always being an exponential. We have a constant A that's going to depend on our initial values. And this would be then the end form of this exact circuit. And that A is found from that initial value. Again, this is kind of how it looks with the voltage. It charges up and then it will be a constant, in this case, of R times I naught is going to be what your end value will be. So general solution is, and this is the same way you do it for the RL circuit. So what you find is that you have this general form where it's this final plus a final state minus the initial meaning 0 plus e to the minus t over tau for both of them. So whether it's an inductor or a capacitor, any first order differential equation always will have this general form to it. So for the RL circuit, it's the same thing, the final value plus the initial, or the final minus the initial. Wait, sorry, I rewrote that wrong. It is initial minus final, sorry. Okay, final plus initial minus final. There we go. And then this is also initial minus final. e to the minus t over tau. The other thing that varies is with an RC circuit, your tau is going to be an R Thevenin times C. So this is going to be your tau. And for an inductor, it's L over RTH. Wait, RTH over L. So L over RTH. And so we also are going to have to find that RTH value. This is going to be found at the final stage. And the reasoning behind this is that, again, it's going to either charge up and then be steady state forever. So you want to know at the end, like, how long this takes. So this time constant is what this tau is, time constant. So what does it mean? So this is an example of a discharging capacitor or inductor. And what tau means is that it helps us to determine when are we defining it's either discharged or it's charged. So you're going to see this throughout electrical or computer engineering, is that there's going to be a gray area of when is it on and when is it off, or when is it fully charged and when is it fully discharged. So we call these, sometimes it will be at 90%, will be that threshold level where you'll say, well, anything, once I reach 90% of the final value, I'm on or I'm fully charged, or 10% at the bottom where I've discharged or I'm almost off. For the time constant, it's at 63%, we say it's actually charged or discharged. So this is just a known kind of constant that we use for the definition of a time constant, is that at that 63%, we say, like, yes, we're actually on, even though it's not fully up to the full charge. It's enough that we say, like, yes, we're on, or we're discharged. So that 63% is that level of determination of fully charged or fully discharged. So that time constant, it is going to be that time. So here's a little bit better one. So here at 60 or 37%, because it's 63% down, it's going to be your tau. So that time tells you how long does it take. So that's useful information. And then you can alter that. If you're a capacitor, how would you decrease that time?
Decrease VS?
So it would be decreasing, remember, tau for a capacitor is RTH times C. So to decrease it, you would either decrease RTH or you would decrease the capacitance. For an inductor, which is that one, what would you do to decrease tau? Okay, so either one, inductor increase, decrease inductor, or increase resistance, RTH. So either way, you have to know what that tau is dependent on. And again, that tau came from the derivation of that original circuit in the time domain. But luckily, you guys don't even have to do that analysis. You just have to find these values and plug them into the final general sort, or not the final, but the general form of the solution.
Will we eventually have to?
In your math class. So I'm trying to remember which math you learn how to do. So separation of variables, I think, is in Math 2250. So you have to do it in there. And then I think you also do, which one?
I was asking if it's in the different linear EQ class.
Yeah. Yeah, so the partial differential equations, which number is that, math?
I
Yeah, for sure in PDAs, but I think you do it also, I think you might do it in 2280 or 2250 also.
2250 is is DE some later on.
So differential equations, so you do some there. And then separation of variables, I think you do in, I think you do them also in 2250. Okay, so you do both. So 2250, you'll get to see that. So because you don't know the math quite yet, all we're doing is really using the form of the solution, which we know always will be that exponential for one. And then we're gonna learn a really handy technique after this one where you can analyze as many as you want, and it's a very easy, simple way of doing it. So, but for now, just understanding this is gonna be time domain, and so we're just skipping to the general form solution and then finding the values that we need to plug into this equation. Does that make sense why we're gonna need to find these values? Okay. Any questions on the time constant and what that actually means? So again, yes.
So at 63% of the time, it's considered charged or discharged?
Correct.
Okay.
Yep, so that is like our level of threshold of where we define the timing. So we can change as a designer, you can change how fast or how slow it's charging or discharging based on moving those values of RTH, C, or L. Okay. Okay, so capacitors. So combining capacitors is a little different. Combine R's. Okay. So equivalent circuits. So for capacitors that are in parallel, I don't have them here. Okay, so parallel capacitors. They actually add like resistors. And for series capacitors, do C1, C2. So this equivalent is going to be C1 plus C2. And for series capacitors, they actually look like a parallel form. So this is going to be 1 over C1 plus 1 over C2. For inductors, a parallel inductor they are like resistors. So L equivalent here will be 1 over L1 and 1 over L2. And then series adds. So you can combine capacitors into just one and then have a first order with them as a combination together. For the resistors, we're going to look at the terminal locations of the time-dependent element, and that's where we're going to put in our A and B for the equivalents, and then we're going to find the equivalents from there. All right, so here we have two capacitors in parallel. So what effect do these have? Does it take twice as long to reach the final voltage? Or does it take half as long to reach the final voltage? Does it take the same length of time to reach the final voltage? Will it have a higher final voltage or none of the above? Which one?
E.
Okay. So we have one vote for B. Anybody else think differently? Do you guys agree? Okay, so we have some votes for A. Anybody else have any other opinion? Okay, so time constant is what is going to determine how long it takes. For a capacitor, what is the time constant? RTH times C, equivalent. And in this case, the equivalent is going to be what? 2C, correct, because you add them. And so that's going to double the time it takes. So it will be A. It's not going to take the same amount because we've changed a value there. And it will not have a higher value. All right, does that make sense? Yes.
So the time constant is equal to like 63%, right?
Uh-huh.
Or we consider time off, charge and discharge. So, if T is like larger, it takes a longer amount of time to reach that 63%.
Yep, correct. Yep, so that form will be, instead of a steeper slope of discharge, it would just be a little bit longer if it takes longer.
Does that mean we can also simplify circuits if we have like capacitors in parallel or something?
Mhm.
Just make it to one?
Yep. Yep, so you can take a more complicated and then reduce it down.
We're confused on how we aren't increasing, like the final voltage or whatever, because if you have like, if you only had one capacitor, you just had an R and a C or VC would be V0, right?
Yep. Okay, so remember,
But if we have two that are the same capacitor, won't they both be VC, which is V0, so the final voltage would be like twice as much, or is that not how that works?
so they're in parallel, right? So the node above it has to be the same voltage, and the node below it has to be the same voltage. So they will both have VC across them, but that's only VC. So if I was to measure this with a multimeter, I'm going to measure that yellow one and the green one, it's just going to be VC. And remember, they're going to look like they're open at the end, so that wire looks the same.
But like what's actually in the capacitor is different.
So they each are storing V0 value on them. So this output will be V0, or VC will be V0, whatever that voltage is. Does that answer your question?
I'll just have to see it a couple of times.
Okay. So think about back to node voltages, and you have that wire all has to be the same voltage on it. So like I could ground this.
Well, I understand that idea,
Okay.
I'm just confused mathematically how the numbers are making that happen, so I think just some examples will clear it up.
Okay. All right.
Something that one of my teammates showed us, which I thought was really helpful, is if you think of it like water, it's like the capacitors are like a tank, and there's like the lip is like a little higher, so that way it doesn't start pouring out immediately. It has to get to a certain height, and then it starts pouring out. So if you think about it with two of them, it just takes twice as long to fill up. But then once they're both at that level, then they last twice as long without the incoming input water. So it's just the same goes out because it's still filling up both of them at the same rate. It just has more tank to fill.
It's a good description. So yes, I like that. Thank you for sharing. Okay, so now let's look at a little bit more complicated circuit. So this looks really scary, I know, to look at first. So we're going to redraw these circuits so that they don't look so scary, because an opener, a wire, looks much easier than the capacitor in there. So we're going to redraw them, as I said, 3 different times. So T0 minus, T0 plus, and a final state. So how you do this is just copy the circuit, and then you're going to look at the switch location and the capacitor location. So you're gonna keep the polarity of the capacitor the same, so this is gonna be a plus on that side and a minus on this side. Then at 0 minus, that switch symbol is first opened and then it goes to a closed position. So before it happens, it's gonna be an open. So we're gonna leave this one open. And then we're going to find this voltage here, VC, across it. So what is that gonna be? It's not gonna be 0. I'm gonna put a ground to have a reference point. So it will be Vs if there's no current flow. Is there current flow? There's actually gonna be current flow here. So I could do node voltage here, and this node would be my VC. So if I do node voltage, it would be VC minus Vs over R1 plus VC over R2 plus R3 equals 0. Or I could notice that this is a voltage divider if I combine those two together. So I could also say that it's VC equals to Vs times R2 plus R3 over R1 plus R2 plus R3. Either way, you're going to get the same equation. And we'll get a value for VC. Yes.
If we knew I, could we also just use like Ohm's law since
Uh-huh.
no current would be going into that open, so.
Yep. So if you knew I, which would be Vs over R1 plus R2 plus R3, you could also use Ohm's law, which would be, so here's your I. So it would be I times that R2 plus R3, or you could do Vs minus I times R1. And that would also get you VC. Because you could take a pathway either direction. Okay, so I'll get the number in a minute because I don't have it right with me. Okay, so for t equals 0 plus, we're going to replace, the switch now is closed because it closes at t equals 0. So we draw the switch as a closed. And here we're going to replace this with the value we just found here, which I'll get in a second, VC. But we know that our initial time, so this is going to be our initial time for the general form equation. We know that it's going to stay the same across here as it did the previous state. So once I find that value, we'll do that one. For the final state, this is again going to be closed. And then this becomes an open. So now what is our VC here?
Yes.
So Vs is only between here and here. So one question, is there current flow? There is current flow, so that is not 0. Is there current flow here? It's shorted, right, from that wire. So there's no current flow there, so all the current flows here, and then it goes back through R3. So all of this is I1. So you could do node voltage again. The node voltage equation would be VC minus Vs over R1 plus VC over R3 because the R2 is shorted equals 0. Or again, a voltage divider, if you see it, is Vs R3 over R1 plus R3. And this will be our final value. I'll get these numbers in a second. For tau, we need to look at the final circuit, so we're gonna again put the wire, and then we're going to take out the element. So for an inductor that becomes a short, this becomes a little confusing. You're gonna take it out and put A to B wherever the location of the capacitor or the inductor is. Now you're gonna take the pathway and find the equivalent resistance between A and B, which means you're also going to remove your sources. So in this case, we get a short here, so our RTH is R1 in parallel with R3. And our tau will be this RTH times C. All right, I will write the numbers down for these, and then next time we will go through the next example. All right, any questions?
Can you go back to the equivalent real quick?
This one?
Yeah, second.
Okay.